Okay, so I want to drag this around to the acid side and the base side. So where are we going here?
The acid is the right side because it's got the O and then the C and then the double bond.
Yeah, there's a C double bond OH. So this H right here is the acidic, and this lone pair of electrons, that's the negativeness. That's where the donation of the lone pair of electrons goes. Um, let's see.
We're getting an echo from somewhere.
I'm hearing it at Rob's, but
I hear yours too. Everyone.
All right, so an acid for the hydrofluoric acid, and then obviously that's a water molecule. And so since the hydrofluoric acid is the acid, then the water is the base.
Mm-hmm.
And so there's a hydronium ion, and there's some fluoride. And so the conjugate acid is going to be the hydronium ion, and the conjugate base will be the fluoride ion. Okay, any questions about those first two? No? Good.
No.
Next one?
this one gave me so much trouble.
Really?
I rearranged it like 14 times, seriously. Like, I kept doing different combinations of each one. Because there were 6 instead of 4.
Right.
So I kept like varying between using the hydronium ion or the hydroxide ion. It was hard for me, at least.
Well, what I was hoping that since this is the section about acids and bases, that it's an acid-base reaction. So
yeah, it makes a water and a salt, but I think I got it partially incorrect. I did the water and the salt or something. I don't know. I think I got one part of it wrong, but I can't remember what it was.
Okay. Actually, this needs to go there, and that needs to go there. Okay, so sodium acetate changes the pH of water. Okay, so we've got acetate, and then a water molecule, and then and there we go. We don't care about the sodium portion of it because it's just going to be a spectator ion on both sides. So the y-axis is the pH, x-axis is the volume, there's the equivalence point, and then this needs to be a pH of 7 because we said it was a strong acid being titrated by a strong base. If it would have been any other combination, then the equivalence point would not be at 7.
Mm-hmm.
The following reaction, ammonia is acting as an Arrhenius base as the hydroxide ion concentration increases. And then it's acting as a Bronsted-Lowry base because it's accepted a proton. And it's acting like a Lewis base because it's donating a pair of electrons. The pH here has got to be between 2 and 3. So it's 2 sig fig, so it's that one. So this is the number that popped up in your calculator, though, but there's only 3 sig fig, so that's not the correct answer.
So then why is 11.11 correct? Because that's 4.
Oh, your only option?
I know, but it really got me when I read that. I was like, well, what else can I fit? But that's not correct.
That's reasonable. Still your own. What else would you have dropped in there for the POH?
I don't know. It felt like it was a trick.
Gotcha. I don't know. Is this to the 11th? Yeah.
Yeah.
No, because then it would be 10.
No.
It's 12.
Yeah, it was to the negative 12.
Match the acid with the correct number of acidic. Okay, so this is
No,
dye.
that's dye. That's dye product.
This
And
one's
that's
the change.
and this
And
one's
that's try.
Alkaloids, common nitrogen, blah 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 blah. What's your loss? Okay, so what should you be looking for? Bitter.
B.
In this case, alkaloid nitrogen containing compounds, they would taste
it's
bitter. All right. They would taste bitter because they're basic. All right. pH buffer can be created by adding a weak acid and a salt of weak acid to the form. When the acid is added to the buffer, what occurs? So when the acid is added, then the salt reacts with it. So the salt of the weak acid is reduced and the weak acid moles are increased. Weak acid moles are increased, salt of the weak acid reduced, because the acid that's added is being added to the salt, which reforms the acid. So I'm going to get more acid, weak acid, less salt. Well, we just need to do the math on this one. So it's just the pKa. 6.35. So actually, it's 7, isn't it? What's the purpose? What's up?
Oh, I'm just. Yeah.
What's the purpose of an acid-base buffer? It's C. We want to maintain, or we want to oppose a change in pH. So I know people want to choose that 7 one, but that's not necessarily the case. If I'm trying to manage a acidic or basic some situation, then I don't want it to be a 7. I just want the pH not to change. It's about, the buffer is about not changing the condition. If you live in Fent, you could add the magnesium sulfate. If you added the sodium acetate, nothing's going to happen because the sodium and the acetate are soluble. If you added the silver chloride, nothing's going to happen because the silver chloride is a solid in water. It's insoluble. So it's not going to disassemble and then have the chloride pull that out of the water, the lead out of the water, and leave behind silver, because it won't let go of the silver in the first place. The potassium and the nitrate are both fully soluble, like the sodium and the acetate, so nothing's going to happen there. The magnesium sulfate is soluble. The magnesium pops off, and then the sulfate finds the lead, and then those two precipitate out. 2-liter container filled with water after 25 grams of calcium hydroxide. What's the pH of the solution? Okay, so you go through, calculate out the hydronium ion or hydroxide ion concentration based off of KSP, and then after you've solved for the X and got your OH concentration, take the negative log of it, and then whatever your answer is, subtract that from 14. So this should be something small, or sorry, not something small, something bigger. Oh, that was a bad question. There was nobody should have gotten that one wrong. Can somebody tell me why?
Because you're adding a basic solution to water, so wouldn't it just be above 7 anyways?
Yeah. So your only possible answer for this one would be B. Yeah. I need to change that one.
There was another question like that later in the test where I'm pretty sure it said like you're adding a base to, it didn't say pure water, but it did say water, but the number was lower than 7. I might have misread it, but
if you add 10 milliliters. Okay, so you get half the concentration because you doubled the volume. So the concentration is half of what that is before.
So why is A not correct and why is B correct?
Because it's the ions, because it's soluble. There is no lithium chlorate floating around in solution. There's lithium ions and chlorate ions floating around the solution.
Okay.
This one, I can't remember.
That's the one.
The
That's the one
PO,
that I was confused about.
the POH is
Oh.
1.6. I can't remember. I think it's 1.6. But you just, calculate the number of moles of hydroxide and then divide by the new volume and then take the negative log of it. Determine the pH. Okay, so this is the XX one. So you need the KSP from octanoic acid. You look that up. You throw that in. Solve for X and then take the negative log of that. This one's just a titration one that we weren't able to do in the lab, so that kind of stinks, but it's just concentration of the acid, volume of the acid times concentration of the base times volume of the base, and you solve for that concentration of the weak acid, and I can't remember what it works out to be, but it's just 0.12 times 46 milliliters divided by 25 milliliters, so probably 0.22. That seems reasonable. Yeah, that's really the only answer it could be. So what's the pH here? Carbonic acid.
It was like 7 point something.
Yeah, I think it was 7. I think it was actually
The
7.0.
the correct answer was 7. Like 7 was nothing. Like 7. But
You know what?
they were
This one was weird because if you put in 7, it said it was okay, but the answer that I put in was 7.0, but it wouldn't it wouldn't accept the 0. It just said, "Oh, that's 7." Like,
yeah, I got really mad because there were 2 sig figs, but the answer was 1 like sig fig.
it would not. But if you typed in 7.0, it still gave you the right answer. Like, it still said you got it correct.
I think I said like 7.1. Maybe I did calculations wrong or something.
Well, it did work out to be 7, and it would take 7 or 7.0. I guess Moodle doesn't understand significant figures.
I said 6.9. I now remember.
So it's the formic acid. The weak acid is, yeah, true. Formic acid has a smaller K, Ka, a larger Ka, so it'll separate more than the butanoic acid. Yeah, and that's it. I don't know what I was thinking. I didn't mean to give you that homework. For some reason, I thought we were going to talk about nuclear stuff this week, but we're not talking about nuclear stuff this week. So just hold on to that. Actually, I'll hold on to it, and then when we
It's fun.
get
Fun about that.
when we get to that in a couple of weeks, we'll pull that quiz back out and your radiation doses that you've received, and we'll discuss why all of those numbers are in there and why living in a certain place means something and why vegetables cause more deaths than radiation, kind of stuff. All right, so we're going to talk about thermochem for a while. All right, so people usually think when we're talking about thermodynamics, we're talking about temperature, and that's not really exactly what's going on here. We're going to be talking about energy, not really the temperature. But to talk about this, we need to talk about like why chemical reactions occur. So chemistry is a central science, but it's built on other stuff, and other things influence it. But the underlying science that everything is based on would be physics. So ultimately, you could say physics is controlling everything. So when we're talking about why things chemically react, we could be talking about, okay, well, this wants to lose a valence electron, so it can look more like argon, or wants to gain an electron, so it can look more like neon or something like that. But we're going to look at it instead of from electrons, we're going to look at it from a thermodynamic standpoint, which is about energy and chaos. So those two principles drive pretty much everything.
Energy and chaos?
Energy and chaos. Yeah. So if something's happening, it's energy based or chaos based. And if nature got its way, nature would want there to be nothing but ultimate chaos,
Mhm.
and nothing would have any more energy than anything else. So not really sure what to say about that, but chaotic and nobody has anything more than anybody else. All right, so where does this come from? So we're talking about the laws of thermodynamics. Okay, so read these three laws to yourself. Okay, so to understand those three laws, we have to talk a little bit about entropy and a little bit about enthalpy. So that first law is about enthalpy, and enthalpy is energy. So we did discuss enthalpy before. Briefly talked about entropy, which is basically a measure of the amount of chaos. So the important thing to remember with that is measuring chaos. So the more chaos there is, the more entropy there is. The more organized something is, the less entropy there is. So this first one, we've already seen this before. Energy can't be created nor destroyed in an isolated system. And so you can make the isolated system whatever you want. The isolated system could be a beaker that you're running a reaction in, or you could be talking about Earth, or you could be talking about, a cat as the isolated system, or you could talk about the entire universe as an isolated system. So if the entire universe is an isolated system, then energy is for the entire universe is stuck. We've got some X amount of energy and that's it. We're not getting any more, we're not losing any of it. So that second law of thermodynamics is really just saying entropy is always going to increase. So if you don't do anything to an isolated system, and that's what we mean by don't do anything, we're talking about an isolated system being something's happening to this thing and I'm not going to stop it from happening. So if I don't do anything to stop it, then the entropy of the system is going to increase. So the the building that you're in right now, if you walked away from the building for like, I don't know, 15 years, what would it look like?
I would have vines and plants all over it.
Probably. What about 300 years?
It would be crumbling and would be gone. Because there
Maybe.
are some like old buildings that are still there, but I guess they're made out of like cement.
Could be.
Yeah,
Yeah, it could be a cinder block building. Okay, so what about 5,000 years?
it would be gone. The like wood houses would be gone, right?
There's only a couple of things that have lasted that long. Does anybody know anything that's lasted into
Ancient
the
ruins of the Greeks and Romans, probably.
sure thousands of
Or
year old
Egyptian.
stuff made with
Marble and
marble with good engineering? So those things could last thousands of years. Anything else lasting thousands of years?
Pyramids.
Trees.
How about really big things like pyramids?
The pyramids.
Yeah, but the trees are not an isolated system.
So how long do you think like something big like the Empire State Building would last? Like obviously the glass would break and stuff, but it's a stable building, right?
It's one of the most stable buildings ever built. So I don't know what to tell you. I can't give you a time frame, but it would last a lot longer than most other buildings, and definitely a lot longer than buildings built these days, because they didn't screw around with that building. I mean, how many buildings do you know come in under budget and ahead of schedule?
None.
So they're like, okay, you have this much money to build this building, and I want it built in this amount of time. And they're like, you know what? We'll take less money and we'll build it faster. And that's what happened with that building. And it's it's well built. Plus, you got all those really cool photographs of those crazy guys walking around with no gear,
Eating their lunch on beans.
Yeah.
Don't forget throwing red hot rivets across large spans of bitumen.
Yeah.
God.
Okay, so in essence, the chaos of a system will increase all by itself. So this is always like some kind of little cartoony thing where like there's a little kid and one of the parents is saying, I knew you shouldn't have been teaching them about thermodynamics because their room is always a mess because they're just obeying the law, the second law of thermodynamics. I mean, if you don't do anything, what's your house look like after a week?
Well, in my
Nothing.
house, I have nephews, so it would be level to the ground.
Right.
Ugh.
So it doesn't seem to take any effort whatsoever to basically make the entire house chaotic. But to organize it, right?
Takes a lot of energy.
At no point have you ever opened the dryer and all of your clothes been folded. Right?
I mean,
Wish.
Yeah.
Very
Yeah.
disorganized. So that's nature. If you give nature a shot, it's going to disorganize absolutely everything.
I shot a bullet.
If you don't input energy into it, then it's going to disorganize everything. And that third law, we're not going to deal with that one very much. Just to understand that if entropy isn't changing anymore, it's because the system is basically stopped. And to get a system to stop, you have to get it to absolute zero. But we can't actually get to absolute zero, so the system won't actually ever stop. All right, so what we need to be thinking about, or another way to be thinking about the reason that chemical reactions occur is from those laws of thermodynamics, you can think about these two overriding principles. That systems tend to attain a state of minimum energy and maximum disorder. So if you allow the system to do whatever it wants to, it will lose all of its energy as much as possible, and it will become disordered. And that's what nature wants to do. So if you cut a tree down and leave it, it doesn't have any energy input anymore. So eventually it's going to lose all of its energy, and then it's going to become disordered. It's going to decay. It's going to break down. Like if you make a cup of coffee in the morning and then you walk away from it, I mean, what happens to the energy of the cup of coffee?
It goes out.
It goes away.
It gets cold.
What
So
happens if you leave that cup of coffee for a week?
It gets gross and moldy.
Sounds like my grandpa used to do.
The milk in the creamer goes bad.
Anything else?
Starts to evaporate.
It evaporates, and when it evaporates, it changes from the liquid state to the gaseous state, thereby increasing the amount of entropy of the system. So all by itself, it's doing what nature wants to do. You don't have to do anything, and eventually all the energy loss and the chaos increase just happens all by itself. So less energy, more chaos. If you don't do anything, if you don't stop that from happening, it's going to happen all on its own.
Energy is still like heat, right?
It can be heat, but it's going to be measured in joules or calories.
So how are we defining energy in this chapter then? Just heat.
Energy will do something. The best way for us to measure it is probably using a thermometer, but not necessarily a thermometer, because like, what were our two versions of energy?
Something that is like heat. I remember heat, and then I remember something that does something like force and.
Throw a word in front of energy.
Kinetic.
Kinetic. How about another one?
Potential.
I think that's
So we have two types. We had this discussion a long time ago, but we're really just talking about the fact that it's either energy that's doing something right now or energy that could be doing something. So when I think about energy, lots of stuff pops into my head, like a rubber band under tension, or a tank that's filled with gas that's, closed off. I could open up that tank and could do something. I could pop a balloon and an energy release is performed. So kinetic or potential. And the units that we're going to use to describe enthalpy are kilojoules divided by moles. And the units that we're going to describe entropy are kilojoules divided by moles and degrees Kelvin. This multiplication is in the denominator with the moles. The abbreviation for enthalpy is an H. There's an H in enthalpy, so hopefully you remember it like that. There's no H in entropy. Although there's no S in entropy either, so sorry about that. We're mixing languages.
Great.
The Germans, or maybe the Austrians, used a word for entropy that started with an S, so that's why we're stuck with that.
You remember what it was?
I don't. German's always hard for me to remember because it's just
Aggressive.
aggressive. That's a well-chosen word. Have you seen that? It's like a 3-minute long video about German words for other words that the rest of the world has.
Yeah.
Like 10 other languages say this word, and they're kind of similar, and they're all kind of nice, and then the German word comes out, and it sounds like somebody's getting their head chopped off.
Yeah, I love it. It's great.
Okay. So the universe is against most things. The universe wants everything to lose all of its energy, and the universe wants everything to lose all of its order. It wants it to become more disordered. If the universe had its way, every single thing in the universe would be a hydrogen atom. They would be evenly spaced across the entire universe, and they would be all at the exact same temperature.
What temperature would that be?
Something very close to absolute zero. So when the battery of your phone goes dead, even if you're not using it, if it's turned off and just sitting there, that's the universe doing its thing.
Oh, interesting.
Okay, so we didn't do heats of formation, did we?
We did kind of. I think we did a lab.
Oh, we did. We talked about Hess's law, the first chapter or first quarter, right?
Yeah,
I
I
forget
just
because
remembered.
this class got rearranged, but we did those Hess's law problems where you looked up. Actually, did we?
I remember doing a heats of formation lab. I specifically remember that title, but I can't remember too much of what it was about.
Yeah, we did. Yeah. Okay. So we talked about enthalpy a lot. Talked about how it's a state function. It doesn't matter how you got there, just as long as you get there. And so then you can do calculations to determine the amount of energy a system takes or gives up based off of where it ends up. So if you know you're starting and you know you're ending, then you know you can get there. You can use other stuff to calculate how much energy it took to get there or how much energy it gave away to get there. So here, a simple example is bromine switching states. So if I go from the gaseous state to the liquid state, I'm looking at 11.9 kilojoules per mole of energy needed to switch from the liquid state to the gaseous state. And so that, I'm sure that makes sense to you in the same way that boiling water takes energy. What's happening to go from that liquid state to the gaseous state? What would we have said? I don't know, I guess in 121. Sorry, 122.
That the bonds are being ripped apart.
Yeah, what do we call those things? Most important thing that people don't know anything about.
Intermolecular forces.
And every single time Sheen answers that question on cue. Thanks. It's intermolecular forces. So that 11.9 kilojoules per mole is simply being used to bust apart the intermolecular forces. Does anybody remember what intermolecular forces bromine would be exposed to?
Uh,
Strong ones or weak ones?
the strong ones. I remember something about friends. Um,
The weakest. The weakest of the intermolecular forces, and those were dispersion forces.
Dispersion forces.
They were
but weren't
temporary
they-
dispersion forces. So those molecules get close to each other and they induce a dipole into each other, and then they can be attracted to each other. But again, it's temporary. You have to be near each other, can't be moving very fast.
Wasn't there another term for that one?
London dispersion forces.
London dispersion. I don't know why I remember France. Yes.
So if I go from bromine to hydrobromic acid, I actually get energy back. So even though I'm a liquid and I'm going to react with a gas and I have to break bonds, I end up getting energy out of it, even though I go a liquid and a gas get turned into a gas. So a second ago, it went from a liquid to a gas and it took energy. But this time, I go from a liquid and a gas to just a gas and I get energy out of it. So something else is happening. What changed?
Temperature.
No, I changed the nature of what's going on. So if I'm talking about reacting bromine, so sorry, let me turn that on. So if I've got two hydrogens and I've got two bromines, on the other side I end up with, some hydrobromic acids. What's fundamentally, this side is fundamentally different than that side. In what way?
Elements versus compounds.
Elements versus compounds. This and this are organized. We get that? All the H's are in one section and all the BR's are in one section. They are not connected to each other yet. And now over here, I've mixed them together. So if you've got some Legos and they're in a box and there's like compartments to your box, and you separate all the blue Legos and the red Legos and the green Legos into their little sections, it's very organized. But then if you let a little kid have access to it, a little kid that's not me, when they're done playing with them, they're all mixed up, right?
Yeah.
So what's happened is I've gone from them being segregated to them being mixed up. So what was the fundamental change? Say again? Chaos changed, right? So I was organized, then I'm less organized. So there's two things that drive chemical reactions. And the two things are less energy, but also more disorder. So those two things can either go together. Like if I have a chemical reaction that's losing energy and becoming more chaotic, then nature's super happy about that. But what if they're fighting each other? What if it's gaining energy but becoming more disordered? Or what if it's becoming more disordered and gaining energy? So it totally depends on what the situation is.
So you know how you always say like chemistry is electron activity?
Yeah.
Is there any way you can relate energy and chaos to electron activity?
No.
No?
No. It's more fundamental than that. But it's also easier to see. Like it's hard to show electrons, but it's really easy to look at this chicken scratch that I have here in the middle and see that I've got hydrogens by themselves, I've got bromines by themselves, and then I've got hydrogen and bromines mixed together. So that's a fundamental change.
Why would a compound be defined as chaotic? I mean,
no, the chaoticness is the fact that they were disassembled from each other and now they're stuck to each other. I don't think you're getting that.
no, I'm trying to wrap my brain around it. It's new, you know.
What's more organized? Your clothes in the dresser and in the closet hanging up, or you wearing them?
The clothes in the dresser.
right? Because like your socks are in a drawer, your underwear's in a drawer, your pants are in a drawer, your shirts are hanging up, but now they're on you, right? So you
Yeah.
just disorganize the organization. So in this case, I've got H's by themselves and I've got BR's by themselves, and now I've mixed those things together. And so
I
I've
wanna
increased
fight
the
the
chaos.
universe. I should be naked.
What?
I want to fight the universe. I should be
No.
naked.
No.
Yeah. You can get
Yeah,
banned
so-
from Zoom really easily.
No, you can get there.
Speaking of Zoom, just for a side second, did anybody notice the new thing in Gmail? Came out like 3 days ago.
Oh, is that their
See?
Meet, yeah, Google Meet.
Oh, they've had that.
Well, it wasn't part of Gmail, so
Oh,
they're
yeah.
realizing that there's an opportunity here to increase their market share for video conferencing, and so they threw that in there, going, "Hey, everybody wants to use Zoom. Well, you can use Gmail. You already have a Gmail. You can just use
Yeah.
this." So don't be
They have
surprised
Google
if soon the college switches over because one, it's free, and
Oh.
two, to log into the class, you would need to go to your MyCGCC, click the link for your email, then it would open up your email, your college email, and then you could click the link within Moodle, or if the instructor emailed you the link, and then it is the Google Meets thing is going to pop up with whatever your name is that you registered with at the college. So then there's no way that somebody's going to Zoom bomb or whatever the meeting, because they can't. You would have had to have given them your MyCGCC information, and then they went through all that process. But what was happening before is people were in the meeting and then they would send the information to a friend who would then pop onto the meeting, and that wouldn't be possible because you would already be logged in. So they couldn't log in as you while you were there.
Sometimes that information can just be scraped as well, and then it would be posted on like a forum or something, and that also is something that occurred.
But then if that happened, you would all of a sudden your video feed would disappear and somebody else's would pop up. But I would see that before they gained access to the space.
You know what I mean? Like someone would gain access to the link through like scraping, and then they would share that link as if the settings weren't configured properly.
What I'm saying is you wouldn't be able to access it without logging in through somebody's Gmail. So they'd have to know the Gmail.
I was saying it was Zoom in particular, and I didn't know that Zoom costed money.
Yeah, you get that 50.
It's free unless you want to do stuff like record things or have a certain number of people online at the same time.
I'm surprised Zoom hasn't been overwhelmed yet.
Well, I've been waiting 5 weeks for a return on a trouble ticket I put in. So yeah, they've sort of been overwhelmed. Okay, so these are standard enthalpies. These are, we've used these numbers before, but can somebody explain to me why the standard enthalpy for bromine is different?
Is liquid its natural state?
Well, look at the other ones that are zeros.
Those are elements.
In their what?
Solid state?
Solid state.
No,
Gas.
I don't know what else to say.
there's a liquid, there's a solid, there's a solid, there's a gas, there's a gas. There are elements in their
Liquid.
elemental state. So if you look on the periodic table, that's what those elements are basically at room temp under 1 atmospheric pressure. So under normal Earth circumstances, the periodic table is telling you that
That's how we find them.
hydrogen's a gas. Oh, that doesn't work out at all. Maybe I'll put it right here. That's dumb. Well, hydrogen's green, so hydrogen's a gas. I'm gonna have to wear a shirt that's a periodic table from now on. It's okay, I have like 6 of them.
Sure. Periodic tables.
Yeah, so
it does say at 298 degrees, at 298 Kelvin.
so that's basically room temp.
Okay.
298 K is room temp because 273 is freezing. So the all of these ones that are 0 are saying that that's just the way it is. That doesn't have any heat of formation because that's its natural state. If I change it from that state, then I've either added or subtracted energy away from it, depending on what the situation is. Okay, so let's look at entropy. So this is sort of like a, well, let's just start with just saying simply that entropy is a measure of chaos. That's it. So if two things become more chaotic, then their entropy goes up. If two things become more organized, then their entropy goes down. This has been something that physicists and chemists have been looking at for hundreds of years. And so this is a little like how we figured, how we came to the conclusions that we have now. And so the first person who gets credit for this is Nicolas Carnot. And he was just a lieutenant in the French army, I think. And he was trying to figure out better ways to make steam engines work. So to move troops and move trains and whatnot. But his steam powered engine is sort of like a, I don't know, the book of Genesis for thermodynamics. The very first word on it, and it up to this point, I mean, there's still stuff in it that people use. It's I mean, it's got a great name too, Reflections and Emotive Power of Fire. So
That's a lot.
he's talking about how you can make an engine, specifically a steam engine, more more efficient. And I've always found this person and this idea interesting because the amount of efficiency that I assumed you can get out of something is drastically smaller than I and probably you would expect. So if you put a certain amount of energy into something, like how much efficiency do you think you get out of that in a typical circumstance?
Hmm.
Isn't it like
60%?
Mm.
Yeah, 60%. Maybe 40.
It's less than 40.
30?
Less than 40? 25.
What he came up with as a perfect engine, if it was perfect, like it didn't have any leaks or it was like insulated perfectly and everything that you could do.
10%.
Did I not have it's right here, it's 36.
36.
So
36.
the maximum amount of efficiency you can get out of a perfect motor is 36%. So think about that for a second, just with your vehicle.
wait,
What's the 64?
The amount of energy
Maximum.
lost.
Uh,
Think about your car. You fill that car up with gasoline. That costs you a certain amount of money. Actually, a hell of a lot less right now than it has for like 2 decades, right? Dropped under $2 a gallon. I'm like, what the hell? I need a tanker truck right now.
That's what we've been doing. We just get a bunch of gas cans and fill them up.
Okay, so the you put that gasoline in your car, and if your car is perfect, everything's working on it perfectly, and it's insulated perfectly, how much of that energy that's stored as potential energy is being used to move you?
about 36%? 34%?
At best, it could be 36%, but it's probably more closer to
20?
sub 20%. Where's it going? Where's that 64% going?
In the air?
Well, be more
The heat?
specific. All right, so heat's going to be lost, certainly. Anything else?
Vibration, like sounds. I remember it was
100% vibration from it's moving. So to move the motor, like if you were looking at a car with the hood open and somebody starts it, the motor moves, right?
Yeah.
Even with the motor just idling, the motor moves. How much does the motor weigh?
a lot.
Hundreds of pounds, right?
We said the same thing.
also like check the notes you did invert them.
Oh, I'm inverting it backwards myself. It's 64% would be the perfect one.
Really?
Yeah.
That's a lot.
It is, but again, the actual value is closer to like 18% out of a vehicle.
Quick question on the history of steam engines. At what point were they at with steam engines? Like, were these double acting using a condenser, just single acting with high pressure steam?
These are single acting high pressure steam motors. Okay, so he writes this book. He's talking, or we weren't finished with that discussion. So the motor moves. So it takes energy to move that motor back and forth. So that's lost. Is the what are the parts of the motor composed of?
And
Most of the time it's metal, right?
metal.
So the internal components of the motor moving, are they helping the car move forward?
No. They're
That
just
that
firing
spinning of that
motion.
thing in there isn't actually making the car move forward. You'll end up making that move the car forward, but that process of causing the pistons to go up, down, and the camshaft to spin isn't actually, I mean, you could just have the car running at idle. The thing's not going to move at all. And so you're losing all of that energy. What about the fact that those parts are rubbing over the top of each other?
So would you like bits, like tiny bits of metal you lost? If they're rubbing against each other?
I guess I was just thinking about friction,
Mhm.
Okay.
losses due to friction. And we'll talk about friction some more. And usually people think about friction being a bad thing, but can anybody give me one instance how friction isn't a bad thing?
Keeps you
Uh,
well,
It stops you, yeah.
and you can walk.
Yeah,
Right?
you can walk. When you're skateboarding and roller skating, the tires are keeping you on the ground.
And you can stop.
You can stop.
The first thing I think of is rain doesn't drive through my head.
Yeah.
There was no atmosphere, and raindrops started at 30,000 feet. By the time they got to me, it would be a water bullet. Right. You'd be dead. Okay, so the Carnot talks about having a heat sink. So if I produce something that's hot and that energy gets used, then the leftover stuff that's doing that has to go to someplace colder. The bigger difference between the heat input and the output makes the motor more efficient. So when is your car more efficient to drive? In August or March? When it's cold outside.
March, yeah.
It's much more efficient when it's cold outside. It actually has to get to a higher temperature to have a decent change in the input and the output temperatures. So I need a sink. All energy plants, traditional energy plants like coal fire plants, natural gas plants, nuclear power plants, all of those things have to be situated near some kind of body of water to sink off the heat. You can't just put them in the middle of a city. One, nobody wants it, and two, there isn't a good water source to cool everything. The next person is Diesel. So Rudolf Diesel, I mean, I'm not sure if you knew this, but he's actually the guy who came up with the diesel motor. I feel like maybe we talked about this in class first couple of days, but I don't remember. Does
No,
anybody talk
because
about?
I would have mentioned like, oh, it's a person.
Yeah, you
That's
weren't.
what I just did.
Yeah, but you missed the first 2 class periods.
I always forget about that.
We have discussion on glow plugs and a few other things.
Anything else? Does anybody remember what fuel source he used?
Corn oil?
Close. Peanut.
Oh my god.
It was the most abundant natural resource that he could find, so he built it around peanut oil. He didn't want to build it around whales because he knew they'd eventually die off if the world was using whale oil, so he tried to use peanut oil, and it works great. And Sheen has probably at least seen some people driving their vehicles around on vegetable oil, right? It works. The diesel motor will still run on peanut oil. You need a couple of extra things like a heating coil to go around the fuel line and a heating coil inside. So you basically need a new coil, a new fuel line, and a new fuel tank. But outside of that, it still functions. Diesel motor works really well with lots of stuff. And if we hadn't found fossil fuels, we would have giant peanut farms everywhere.
So, but I thought it.
Go ahead.
I just like, wouldn't that ruin a car?
Wouldn't what ruin the car?
Peanut oil. I guess not. I mean, if
Why would peanut oil ruin the car?
I mean, what's like? Why would we not? If it's like so abundant, why would we not run off peanut oil instead of what we're using now?
You think peanut oil is more abundant than diesel fuel?
Well, it will be, or it could be. I mean,
I do not disagree. At some point, there will be more peanut oil in the world than diesel fuel, but that's a ways away. But what I'm saying is, if we would have just taken his idea to heart, and instead of, drilling for oil, and we would have just planted peanut trees, we could be there. We could already be at the sustainability.
Peanut grown underground.
Yeah.
They're grown underground?
Yep.
I thought it was like a small tree, no? Oh, even better.
So they live in lagoons.
Less pests, right?
Funny.
Does anyone know if peanuts are a big crop?
If they're a what? If peanuts are a what?
A mixer?
Stop muting yourself.
Nitrogen fixer, and I'm trying to tab out so I can make it up.
It's a lagoon, so probably.
Lena says yes.
Yeah, they have some bacteria.
Neat.
Rhizobium.
Okay, so first person is Nicholas Carnot. Next person is Rudolph Diesel. Blah, 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 blah. Next person, you probably know this guy's name. And this guy's name. They did not like each other. Both of them thought the other person was stealing from the other one. And so when they're describing the second law of thermodynamics, Kelvin says it's impossible by means of inanimate material agency to derive mechanical effect from any portion of matter by cooling it below the temperature of the coldest of the surrounding objects. And people read that and were like, all right, I have to read this like 6 more times before I understand what he says. And then Celsius, the entropy of the universe tends to a maximum. So straight up saying the entropy of the universe is going up. So as far as like a Neil Tyson stuff, chaos. Sorry, not chaos. Cosmos. How does this apply to, say, something like Cosmos?
The universe is always expanding.
Right, constant expansion. The universe is getting bigger and bigger and bigger, and so they're flat out of the gate. We don't know this yet, like on an astronomical. The astronomy for this hasn't been perfected, but we already have that this is probably what's going on. So this led astronomers to somebody know what they were looking for to determine that the universe is actually what's our biggest indication.
Blue shift?
Say again?
Isn't it blue shift?
Yeah.
Just the Doppler effect on light.
The Doppler effect on light. So the Doppler effect, you know it by like a vehicle with a horn or a train, and the sound actually changes pitch after it goes past you. That same kind of thing happens with light. And so if everything's moving away from us, then the colors that we're seeing shift in the same way that something moves away from us, the sound shifts. So we know from the Doppler effect that all the stars in the universe are everybody separating out from each other. So you end up with the idea that this is an constantly expanding universe.
Isn't there like a Doppler radar or something?
Yeah. Yeah. Same situation. Just checking to see where stuff is in the atmosphere. Okay, so in this case, the German is super easy to understand, where the Scottish guy not so much. Anybody know any actual Scottish people?
Yeah.
Knew a few content creators from Scotland.
Same, but like not personally.
It's hard to understand them most of the time.
Mhm.
Yes.
There's a nice YouTube video about them putting Siri in an elevator with, and the two Scott guys have to get the elevator
Yeah.
to go to the correct floor, and it doesn't understand them because it sounds so like such poor English. Okay, so moving forward, then the next person is Ludwig Boltzmann. So Boltzmann is the person who basically takes all of this information and puts it together in a way that you can use mathematically. So you can do calculations based off of Boltzmann's work. So he has this equation, and so it ends up being called the Boltzmann equation. So we've got S being the entropy, W being possible microstates, which we're going to have to discuss, and K being Boltzmann's constant. And Boltzmann's constant is just a combination of the ideal gas law and Avogadro's number. But the ideal gas law in terms of joules instead of liters atmospheres, you just multiply the liters in the atmospheres and you end up with a joule value for the energy on the top. So you can write the ideal gas law constant two ways. So you anyway, you end up with another constant by just putting those two constants together. All right, so
are we just using the 1.38 times 10 to the negative 0.3, or
maybe
are
depends on
we
the
gonna have to
situation.
write
The Boltzmann's constant,
or no? Are we gonna have to write the whole thing, the ideal gas constant
0.026?
divided by?
Probably not. I'm sure it's just going to be there. Okay, so let's talk about microstates. Boltzmann would absolutely be banned from entering the state of Nevada, because they wouldn't want him to be anywhere near a casino.
Mhm.
Mm-hmm.
He would crush the house. So what is he doing here? So he's trying to describe chaos. So think about that for a second. You're trying to describe something that's inherently indescribable, and he does a damn good job of it, which is why he's got the equation. He's got the unit named after him.
Did you get a Peace Prize? Or a Science Prize?
You mean
Science prize.
You mean a Nobel Prize?
The Nobel Peace Prize, yeah.
Okay, wait a second. I just want to clear a little bit up for you. The Peace Prize is one of the Nobel Prizes.
Yes, I understand that.
Why would he win
And
it?
my question,
Why would he
Well,
win the
'cause
one about peace?
I've like seen so many scientists winning the Nobel Peace Prize.
One.
It's the most,
One.
okay.
They usually win it for chemistry or physics or medicine. So what he does is he creates some drawings. So all of the chaos stuff is a little bit easier to understand for people. And so he says, all right, so what we have here are microstates, and which microstates are most possible. So he's got this box. He's got 4 different colors in this one box, and there's an adjacent box with nothing in it. So which one of these things are most likely to happen? All of the different particles in the same side? Or is it more likely that it's evenly distributed?
Evenly distributed.
So you can look at all the different possibilities for even distribution. So those are the different positions possible. So this kind of looks like dominoes.
Dominoes.
Yeah. So doing this, he's showing that these are the different possible chaos states for a particular substance. If you want to apply it to just dice, then what's the most common thing that you're going to roll with 2 dice?
The bottom row or the top row?
7.
No, it's a column you need to choose.
Oh, so then the
7.
7.
Right? More like, what are the chances of 2 dice? What are the chances of you rolling a 7? It says right there. It says right there. It's right there. I'm going to unmute all of you.
I'm just
1/6.
1 out of 6 are your chances of rolling a 7. So they obviously drop from there. So the chances of you rolling snake eyes, or if you're Yahtzeeing, trying to get double sixes, or cribbage, right? Double sixes are awesome. Any doubles are great, but 1 in 36 possibility of catching that. Why is that? Why is it 1 in 36?
Because it can only happen one time. Like, the 2 die have to be the same number.
maybe there are 36 different combinations, and we can.
How about this? What are the chances of you rolling a 6 with 1 dice?
1/6.
1 out of 6, right? So what are your chances of rolling a 6 with 1 dice?
1/6. So you just want 7.
So 1 out of 36. That's how it works. Okay?
Got it. It's a total.
So it's a lot less for the 7, because you could roll a 1, a 2, a 3, a 4, a 5, or a 6. Any of those numbers on the 1 dice is what you need. Does that make sense? So on this 1 dice, I have a 100% chance of rolling 1, 2, 3, 4, 5, or 6. And so what's the chance that I'm going to roll the other dice that I need to go along with? Let's say I rolled a 2. It's a 1 in 6 chance for me to roll the 5. Does that make sense? So this is what Boltzmann is explaining to people about chaos. So the reason I'm saying he wouldn't be welcome in Vegas is he would know exactly what the odds were calculated in his head as to if he was going to get the card he wanted or if he was going to roll the dice that he wanted. And then he would literally just play the odds and walk away when it wasn't in his favor.
Ask a question.
Sorry, a truck drove by. I didn't hear that.
Helena said, "Is that why 7 is the lucky casino number?"
7's the lucky casino number. It totally is situational. You might want to be rolling 7s, or you might not want to be rolling 7s if you're playing like craps or something like that. I guess it just depends on the situation. I mean, if you're gonna play anything at the casino, what are you supposed to play?
The penny slots. That's what my grandpa used to play, and he got the rich.
Yeah, that's what we do.
It's blackjack.
Yep.
Blackjack.
I can't play blackjack.
Is blackjack the one where you're supposed to get to 21?
Yes.
That's a fun one.
Well,
I play that with my friends without the betting part. It's a fun game.
the house has the worst odds. I mean, they still have the odds, but they've got the worst odds.
I thought the house has the best odds because I almost
No.
at least my friend Austin is always the dealer and he always beats me.
Did I say that incorrectly? That of the odds of all the games that you can play, the odds are the worst for the house playing blackjack. They're the best for you playing blackjack. Does anybody know what game is the worst for you?
Isn't it roulette?
It's 1 out of whatever the hell it is. Is it 37? I think it's 1 out of 37 because there's a 0.
Is that the game where there's like red and black sections
Red and
and
black
you put
and
a
1 green.
and you put a marble in it?
Well, you don't. It does.
The dealer does. No, because I've seen those, but I've always wondered what they were.
It's just a wheel that spins. They throw a marble. It runs around into the opposite circle, and then wherever it stops, wherever it stops.
Yeah, why would you play that? Because it's such a specific. You have to guess so specifically.
You can guess whether odd is going to be an odd number, even number, red or black.
Or black.
You can pick the first third of the numbers, like you can pick 1 through 12, but then your odds shift on, you know, if you're asking for more chances.
Yeah, you're winning depletes the more chances.
Why? Because if you put $1 down on 16 and it comes up 16, how much do you get? 36 bucks.
36 bucks. Yeah.
So it's that's why. I mean, even that is bad, right? Because there's 37 possibilities. So even if everything works out perfect for you, you still lose. Okay, so how does all of this apply to, you know, molecules and whatnot?
Because chaos, I mean,
I want you to think about these containers being gas containers that are connected in the middle by a valve. And if you open up both sides of the, if you open it up so the gases can pass back and forth between each section, the highest amount of odds that you're going to have 2 of the molecules out of 4 of the molecules on each side. That is the highest odds. The chances that all 4 of the molecules are going to be on one side is going to be slim.
could that actually happen?
It will. It has to happen. Like
Yeah,
that possibility is there. The chances of that roulette ball landing on your number is there. If you sat there for the entire day and kept putting $1 on number 16, it's gonna pop up eventually.
yeah.
This always reminds me of the first class I took, the first statistics class I took, and our very first assignment was take a coin and flip it 500 times and write down your result for every single one of them.
Ugh.
So he never graded them other than the fact that he glanced at them. Does he know, how did he know that the person didn't do what they were supposed to do?
Yeah, they could have just written heads, tails, heads, tails.
So how did he know that?
What the end percentage was?
No. He just looked to see in this list of 500 face up, face down, or heads or tails, if there was a long section of, say, 12 in a row that were tails. If he didn't see that, he knew the person cheated, because it's going to happen. By cheated, I mean didn't actually flip them and just wrote down 500 heads / tails. It doesn't make any sense if you're doing that and you're cheating and you're just writing down. Nobody's going to write tails 12 times in a row. But in reality, if you're flipping 500, you're going to have a section where it's the same for 10 times in a row. So if we want to apply the chaosness to different states, what state is going to be the least chaotic?
Elemental 4? Or, solid, right?
Yeah. The least number of possibilities for the position of the molecules is solid because they're stuck in a fixed position. The highest is going to be gases because they're going to be flying around inside the container and they can be anywhere. And liquids are going to be somewhere in the middle.
Isn't there like a 4th state, like plasma?
Yeah. I mean, sure. Plasma is just the electron left and came back.
Oh, cool.
When we talk about radiation stuff, which I thought we were going to do today, but we're obviously not, we'll talk about that. Okay, so we already talked about the fact that if I take 2 elements and I put them together and they form a molecule, I've got more chaos there because I've just mixed the stuff up. And in the same way that the intermolecular forces for London dispersion become stronger as the molecule or the atom gets larger, same situation happens with entropy, because then we can talk about the electrons themselves. So if we look at the first, if we look at that noble gas column, these S's go up as the molecule or as the atom gets bigger. So why is the helium, why does this guy have the smallest entropy of these noble gases?
It's the lightest gas.
It's the what?
It's the lightest.
No, what do you mean by it's the lightest? Mass doesn't really have anything to do with it.
Doesn't have as much energy.
No, the energy itself isn't a function of entropy. Think about, I mean, what's around a helium atom? I've got 2 protons in the nucleus, and then what's around it?
2 electrons.
2 electrons. And they're very close to the nucleus, right? So what about the neon? It's bigger, right?
More than just an S shell.
It's more than just an S. I've got an S and a P. Now think about the shape of that neon. It's a pretty tight sphere, but because it's got 10 electrons, that sphere can be shifted. So its shape can be a little bit different. The position of those electrons can be different. And what happens when I make it bigger? And I'm into energy level 3, or energy level 4, or energy level 5. When I'm down to xenon, I've got a pretty big atom. So that atom can be squished. And we had this discussion with the dodgeballs, right?
Mm-hmm.
So the biggest of those dodgeballs can be squished and deformed. So that's the situation here. The xenon is the largest one, so it can have different shapes relative to a helium because its larger form can create, you can have a bigger disparity. So I can only squish the helium so much, where the xenon can be squished a lot more because it's a lot bigger. If I had a marble-sized piece of Play-Doh and I hit it with a hammer, it would be a certain size. But if I had a softball-sized piece of Play-Doh and I hit it with a sledgehammer, it would be a lot bigger, right? The shape would be bigger. So same situation with the molecules. They can be very similar to each other, but if they're larger, then they can have more possible shapes. So that would be more possible chaos associated with them. Alrighty, so we want to talk about spontaneous reactions and what that means. So that word spontaneous, just in general, what's that mean to you?
Spontaneous, like quick, out of nowhere.
Quick or out of nowhere? Anybody else?
I think of like someone spontaneously catching on fire.
Yeah, that's not a thing, but okay.
I mean, it's happened. It really has. Well,
No,
it
hasn't
seems
happened.
like it was.
It can't happen. Can somebody want to tell me why a person can't spontaneously catch on fire?
Needs to be
There's no energy going into that. Nothing sparks it.
Because you're 70+% water, and water is not flammable. So remember what the ratio needed to be for alcohol and water for the alcohol to catch on fire?
Run? Yeah, run.
It needed to be, man, that's just bad. It had to be less than 25% water for it to actually catch on fire. You're at 70+% water, so can you catch on fire? No.
I've seen some of those things before.
Of a person
Quite weird.
catching on fire?
No, not really catching on fire, but just like someone turning into ash and like their fat being like put into the floor and like their body just leaving their hands and their feet before.
Okay.
Yeah,
Mary Reeser was one of the famous ones.
But
Thank you.
but a match wasn't put to the person's skin, and that was the end result. What had to happen for that to occur?
They had to die, they had to start producing methane, and then something had to light that methane, causing their fat to wick.
Or they can be hit with an accelerant. So, do you guys know about busting into a castle? Ways to bust into a castle?
Trebuchet.
Anything else? I like trebuchet. Anything else?
Catapult.
It's got something to do with what you're talking about right now.
Light it on fire.
What are they lighting on fire?
The wood door.
No.
The catapult, the things on the, that they released with the catapult.
All right, I'll take that as nobody gets this one. I'll look down. No, nothing in chat. Okay, so
Looking inside, right?
you dig a hole underneath the interior wall. All right.
Undermining the integrity of a wall. Okay.
No. So dig this hole, this tunnel, so you're sure you're inside of the space. Then you fill that space with pigs. Then you put an accelerant in with the pigs, and then you light it on fire. Pigs
That's horrible.
lit on fire. So the fuel source is the fat from the pigs. It creates so much heat that it causes the ground to be unstable and the ground to fall in, and then the wall falls because they produce a sinkhole.
Nice.
Not something that gets talked about a lot in history, and I've only seen a couple of movies where they've discussed it, but flaming pigs definitely breaks into castles.
That's kind of horrible.
But again, it's disgusting.
Did they at least kill the pigs first? God.
Probably not.
It's a whole new meaning to it.
There's a video out there of in China they have a whole bunch of pigs that they were tainted with can't remember some kind of disease, and they just put them in a pit, throw on an accelerant, and the fire burned for weeks.
Please don't say stuff like that.
That's
gross.
disgusting.
Sounds like China.
Okay, well, yesterday, 2 million chickens were slaughtered in Maryland.
Monroe. I'm kidding. I'm kidding. It's a joke. Oh my god.
Anybody have any idea why
Okay.
they had to slaughter 2 million chickens?
Why?
Because they got COVID?
No.
Because they needed more food?
Because I don't know.
Oh, no
because there's
demand.
no demand for food.
That actually
yeah.
makes sense.
No. No.
What is it?
They were slaughtered, and that was it. They were
Because
killed
we need the
and
meat.
sent to the dump.
There was
Oh,
no
really?
reason for it?
Were they tainted with something?
No,
There was absolutely no reason for it.
there
What the
was a
hell?
reason. You don't kill 2 million birds for no reason.
Okay, well, what's the reason?
Nobody at the slaughterhouse can do it. There's two things. Kalina's got one thing. There's less of a demand for food, and there was nobody at the slaughterhouse to do it. So they literally just took them out and killed them. They had to go to waste because there was no way to dispose of the bodies in a way where they could save the food. And here we have food insecurity, and we're wasting it. Same situation with fruits and vegetables, right?
Great.
See the
I
potatoes
feel
and
like
whatever.
Or the milk.
I feel like there was a better way
The
to do
millions
that.
of gallons of milk that are being dumped onto farms because the schools are closed, so kids aren't buying milk at school.
Mhm.
So there's no place for it to go, and there's no way for you to store it. There aren't facilities that you can just roll in tanker trucks of milk and freeze them. Yeah, we're ill prepared for this situation.
Yeah.
Is any of it being dumped in places that collect biogas?
That would be smart. So the answer is no.
Yeah, of course.
Okay, so do we have an answer for spontaneous reaction?
It does not occur without a cause.
Doesn't occur without a cause. So it's a reaction that will continue to occur. So you don't need to constantly have input to get the reaction to occur. So if you start a piece of paper on fire,
Yeah, like use a match to light a paper on fire and then it just burns out.
okay, so that burning of that paper is a spontaneous reaction. All right, so go ahead.
My question is the spontaneous reaction when you put the light to the fire, or whenever you don't need the light anymore and it just does it on its own?
When it does it on its own.
Okay.
So you might need what is it that we're needed to? Why the match?
Because it has fire on it and it starts the reaction, it gives it the heat.
Input energy, yeah.
What do you need the input energy for?
Break the first bit of
To
bond.
break the initial bonds.
What did we call that?
Oh god, the heat,
Do you remember this?
energy evacuation?
Yep.
Activation energy?
The activation energy. So I just need to overcome the initial like friction. You could say friction. Have you pushed something that was very heavy along, say, like a concrete floor? And initially, it's like I can't get this refrigerator to move, and then as soon as it starts moving, like, oh, I don't need to push nearly as hard, and it keeps rolling. Does that make sense? Same thing with a car. Like the car is hard to get moving, but once it starts to move, then you've overcome the initial static friction coefficient, and now you're having to overcome a kinetic friction coefficient, which is a lot less. If you're driving your car and it starts to slide, it's hard to get it to stop sliding, right? So it's hard to get it to slide, but once it is sliding, it takes a lot more effort to get it to stop. So once I overcome that initial amount of energy that it needs, then it just happens on its own. All right, so the person who gets credit for this idea of calling a particular reaction spontaneous is Josiah Willard Gibbs. He's the most important physicist slash chemist that people don't know. He's American. He has written books that are still taught in engineering classes. He wrote math books, physics books, chemistry books, and engineering books. And his engineering books are still literally like, yeah, read this 200-year-old text because, all right, 150-year-old text because it still applies to everything that we do now. If you read his text and follow his work, bridges will not fall apart after they've been built.
When did he? When was his like existence?
1800s.
Oh wow.
So he was, I think he was 19 when he was accepted as a professor at Harvard.
Seriously, 19 years old?
He got his PhD at 19 and they immediately like hired him. But he was very quiet, bad social skills, didn't like people very much, just sat in his lab and did work. And he lived with his sister. So Harvard gave him a house on campus to live in, and his sister moved in with him to take care of him. She ended up getting married, and the guy she married was like, oh my God, you're the smartest person ever. And he took all of his work and published it in a journal that he wrote, that he edited. So basically,
the husband edited?
That the husband, so his brother-in-law. So the journal wasn't known to very many people. It finally got a little bit of notoriety in France, where this guy here, you remember his name?
Where's he at? Oh, yeah.
So this is the equilibrium guy, right? Le Chatelier's principle. So Le Chatelier reads this paper in this obscure New England journal and is like, this is amazing. And then starts telling people in Europe about all of Gibbs' work. So he got a subscription to the journal. He got it every couple of months. He would read it. He would teach it to his students. Like immediately, he would teach this information to his students and then disseminate it to other people on campus and to other universities. And then finally, there was a conference in Europe and the Americans came over and he was doing a seminar and they're like, oh, this is great stuff. Where are you getting it from? And they're like, Gibbs at Harvard. They're like, we don't know who Gibbs is. And they're like, how do you not know this guy in your own country? And we know him. Because again, it was a very obscure journal and the brother-in-law was basically taking advantage of him. So in the end, his work ended up causing everybody to understand this concept of spontaneity. And he called the relationship of spontaneity something called free energy. It ended up getting renamed Gibbs Free Energy, obviously after him, and then they changed the symbol for it to a G. But what he was trying to do, Gibbs was trying to come up with a mathematical way. Gibbs wanted to turn these two statements into math. He wanted to be able to take this and say that reaction is spontaneous with math. Okay? So here's Gibbs' equation. And it turns out to be really easy. I've got two terms. One I subtract from the other, and one of the terms is multiplication. That's it. This is the whole equation. So Gibbs free energy is equal to the change in enthalpy times the Kelvin temperature times the change in entropy, which is exactly what nature is looking to do, right? Nature wants to change the amount of energy and wants to change the amount of entropy. Does that make sense?
What
So
does the G stand for?
Gibbs free energy. So
Okay.
what he's saying is the G is the amount of energy that's freed or the amount of free energy that you need.
So it's Gibbs free energy is equal to the change in enthalpy minus the change in entropy
times temperature Kelvin.
times temperature Kelvin.
Why is there a delta in front of the G?
Because this is a chemical reaction, and so there's a change of the species. So
Okay.
if I'm talking about something simple like hydrogen gas being reacted with water, oxygen to produce water. So these things right here have a certain amount of H, and this has a certain amount of H. We okay with that?
Yeah.
And these things have a certain amount of S, and this thing has a certain amount of S. So how did the S and the H change? So you'd have to do a little calculation on that. There's basically some addition and some subtraction, and then you'd figure out what the change in the enthalpy is from reactants to products, and the change of the chaos from reactants to products, and then you could use this equation to figure out what the overall effect is. So what he's trying to do is, nature wants this to go down. We okay with that? What does H stand for?
Enthalpy?
Which is a representation of what?
Heat?
Or energy of a system.
Energy.
So nature wants the
Energy.
energy of a system to go down. All right? And what does nature want to happen to the entropy?
It goes up. because
Nature-
it's chaos.
Nature wants chaos to go up, so nature wants the S value to go up. So
Is it also a change in temperature, or is it just a change in entropy?
it's not a change in
multiplied by-
temperature. It's the changes that are occurring at this particular temperature.
Okay.
You can change the temperature and change the effect, but you only you do this calculation at a given temperature. Then you can change the temperature and do it again if you want.
Okay.
All right. So if the reaction is spontaneous, can you give me the sign, positive or negative, for delta G?
Wouldn't it be positive?
Well, what does nature want to happen to the entropy or to the enthalpy?
Goes down?
Okay, so if I made the enthalpy go down, right? Tell me what the delta H is going to be.
Negative?
Negative, right?
Mhm.
Because if I've got, let's say I'm looking at delta H here, and so it's H final minus H initial. Are we okay with that?
Yeah.
It's what I started with. I subtract what I started with from what I'm at now. So the same thing with your checking account, right? At the beginning of the month, if your checking account had $1,500 in it, and at the end of the month, your checking account, or the beginning of the next month, your checking account has $1,700 in it, you had a change of plus 200, right? Everybody good with that?
hmm
It's not like you earned $1,700 over the course of that month. You only earned $200 extra because you started with $1,500. So if this value here, if the F, if the final entropy, I don't know, I'll just make something up, is 20, and the initial is 10, then what's my change?
10?
10.
Negative 10?
Positive 10,
Positive 10.
right? So that means energy went into the system. Does nature want that? No. Nature
No, it
wants the
wants-
energy. Nature wants the energy to start at 10, start at 20, and then end at 10, and giving you a negative value. So if this value is negative, nature's happy. But what about the entropy or enthalpy value?
It should be positive, but is it going to end up being negative?
No, nature wants this to be positive because then that means S is going up. So nature is hoping that the energy goes down, so a negative delta H, and the S goes up, so a positive delta S. And so that would result in a negative delta G. So if the reaction is spontaneous, you get a negative delta G. So when you light that piece of paper on fire and it's continually burning, why is it continually burning? Because it's giving off free energy. How do I know it's giving it off?
because that's what this negative means. That means that the system is giving away energy, not taking energy. If it was taking energy, then it would be a positive value.
Did we also say instead of giving away energy that it's losing energy, or is that different?
That's fine.
Okay.
Either is fine. Make sure that you do all these calculations in Kelvin.
Yeah.
Okay. I think I'm gonna call it for a day.
Are we gonna have those problems on the homework? The
No,
equation we just did.
no. I mean, maybe just the equation, but no calculations from it yet.
Okay, cool.
Does anybody else get tired after these things?
Yeah.
Yeah, I'm always tired.
Why?
I get, I don't know. I get a good